Good evening. Saturday, May 13th, 2023. On Friday the 13th, which is considered an unlucky combination of numbers and days. Sometimes, besides something like numerics or mathematics, there's numerology, right, where certain numbers are considered fortuitous or not, or as to what they refer in the symbology and symbolism. Kind of like the Trinity is, the Holy Trinity of Christianity, for example, or otherwise it reflects, like from the Dictionary of Symbols from J.E. Serlo, any various measures that come together, the trinary, the tripartite, anything like that, the tripos, that which will stand a stool or a table or da da da. 1 and 2 is me and you, or each other in a sense, and there's 3, and then like 4 is number is like, who is 4? Well, that's the priestly caste or something like that. Well, who is 5? That's the priestly class or something like that. Who is 6? Well, that 6 is like the marshal. And what is 7? Well, 7 are lucky, beautiful people. How about 8? Well, it varies, because 8 is considered lucky in for example, in the Orient, and a number like 888 is considered the most lucky or something along those lines. Whereas 9 begins to get a little sketchy, and it just kind of depends. The cat has 9 lives and this and that. In terms of then, 13 is considered unlucky. And not just because it's a prime number, but for some whatever triskaidekaphobia comprises it to be. And then there's 21 is considered lucky because it's 777, or 555 is considered lucky because this is a triple nickel or something like that. So these fortuitous numbers are just kind of thing. I have somewhere a book on medieval numerology, and it's kind of gets into the interpretation of things, and then trying to figure out how to associate things with numbers, because the numbers were considered kind of mysterious and full of symbolic meaning, and it is so that they are, and that they convey meaning and that kind of stuff. There's a traditional study in the Kabbalah and the mystic tradition as of the Talmudic called the gematria, which is kind of like after the tetragrammaton, which is like 4-letter combinatoric enumeration of names of the deity. Then there's the gematria is kind of a numerology of sorts. And so it's similar as one that's the fortune-telling tradition called astrology. And what's astrology? Was like according to when you're born in the stars and the current position of the stars, then it attempts to tell each person their fortune. And so in a sense, these things are just geared toward people who were willing to believe what they read as the fortune is true. And so it's self-fulfilling in that sense. But another one is kind of like this, is that everybody is born, usually in a given region where the astrology of their signs are in effect, right? And so at given particular times of their perceptual and postnatal development of their life, there's very particular stages with regards to extroversion or introversion, say, or some other personality characteristics. So somebody is born in the summer, when they're 6 months old, it's the middle of the winter. And maybe in that world, then there was nothing to do but stay inside. So their entire socialization and acculturation at that particular critical period was like so. And for somebody who's born in another type of the year, at 6 months, it would be totally different. And so it just kind of reflects different kind of upbringings, just in terms of the people are born in clock time and calendar time and on solar time. And then it ends up being that according to that, then that's one way to look at astrology according to the signs that follow the zodiac, or the positions of constellations in the sky at given points of times. Those reflect that association, that numerology, that in this case in astrology, and giving some ideas that there's in a sense some grain of truth in it, even if it's only phenomenological, even if it's only semiotic, even if it's unscientific, is the way people think. So it's a very study in itself. And it could be that then there's also, it's the way people develop, so it's a very study in itself. Now that said, then there's also particular, like individuals' horoscopes, is like what exact day were they born and what were positions of all the objects in the heavens, what do they mean? And so that'll vary from person to person, I'm sure. And then there's also in Orient, there's also the zodiacal of years, like in the 12-year cycle or so. It's a similar sort of conceit. So anyways, put all that kind of stuff aside, the symbology of things, what I've been looking at studies more is the differential equations. And so what I've been looking at is 1 over x. And last time what I was talking about, and I'm quite taken with this idea at this point, is this idea, is that 1 over x in reduced and restricted to the first quadrant. So by the first quadrant, I only mean a function in one variable where the domain and range are positive. So in this case, it's simply considered the usual xy quarter plane, or the quadrant, and how the quadrant is usually used for stuff like, in analysis about the circle and trigonometry and sine and cosine in terms of the angle formula and the triangle and trigonometry and the circle and the quadrants and the reflections about sine and this kind of stuff and the even and odd, ... So I'm really interested in is the inverse function 1 over x. Y equals 1 over x. So here we'd often describe a function as f of x equals 1 over x. But here I'll kind of just read it as y equals x or f equals x. Because in this case, in the same time that y equals 1 over x, there's that x equals 1 over y. That the inverse is so solving for either side of the variables gives us an expression in terms of the other variable. And so it's sort of this interesting case where solving the variables in terms of each other gives the same kind of function if you erase the values of the variables and just have a placeholder for the variable. So anything that's symmetric in the first quadrant as about a line through the function x equals y is like so. And similarly, any function that's like so is symmetric about x equals y in the first quadrant, or the positive numbers. Functions of the positive numbers, including zero, are exclusive of 0, and out towards infinity in the unbounded. And for a point at infinity, whereas infinity, it's infinitely far away, you can point at it. And it's at the point at infinity, according to matters of perspective, from wherever you are in terms of the origin, which is anywhere you point, according to the existence of an axis or something. So anyways, the idea is that this inverse function, I've been looking at this Fourier series. And so Fourier series basically have for a half period the idea that there's a cyclicity, there's cycles, the periods. And so each period, this function goes in a sinusoidal wave over the axis, and then below it, the negative part, and they're reflections of each other. If you were to translate the first half a period to the second, and then it would be symmetrical, it would reflect each other. If you were to make a shape like so, it's like an even function, or if you were to consider it in the period being between negative pi and pi, it would be an odd function. But via this manner of translation, it's an even function. So what I think about is this. Now imagine if you take like a sinusoidal curve like that, and then turn it counterclockwise one quarter revolution, so basically what was horizontal is vertical. And then tip it even further, a little bit farther, so for three quarters revolution, and now it's bowed out downward into as if it were sitting in a quadrant. So now just block that out with putting a line through the middle of it, which would be symmetrical, and aligning that with x equals y. And so then what you see is the shape that basically in the first quadrant comes from infinity of the one axis down through a value on the x equals y line, and then out in a reflection, symmetrical, is about x equals y on down. So the idea is think of that. So then think of 1 over x, which is a function which is just down from infinity through 1, 1, and then out to infinity, and symmetrical about x equals y. Now turn that 3/4 of rotation clockwise, and what you could see is that's just kind of a hump of a half a period. Well, yeah, but the points are out in infinity. And if you shrank it all the way so that it was just kind of filling that same space, that it would be an infinitesimal difference from otherwise just straight lines, like It's just basically saying it would be just like a straight line sawtooth wave. It's called sawtooth when it's like the teeth of a saw, which are angled according to their kerf and other various technical descriptions of the blade and the teeth of a saw with teeth, a ripping saw, as it were. And there are various technical definitions according to practice of the application of the wood saw, the hand saw, vis-a-vis that there are saws with no teeth really, but they're called knives mostly, and that there are saws with teeth that have like curvature teeth or different kinds of shape. But the sawtooth wave basically implements a increasing and linearly and decreasing. Yet the point of this tooth is smooth, not a kink. It's not a right turn, as it were, of the increasing advance or the front edge of the tooth and the back edge of the tooth, because it's as of scaling that down. So it's basically arbitrarily cornered there, smooth, but the curvature there is arbitrarily small, because the circle that would represent being that in the infinitesimal is arbitrarily small. It's like that 1 unit square, as if 1 over infinity of that, right? So this kind of non-standard approach, meaning non-standard, what do you mean non-standard? Well, it's the limit of a continuum of functions, and then you're also applying some analytical character that's outside its box. It's non-standard, but still keeping it real in terms of analytical character. So anyways, if you think of the Fourier series as being a sum of sine and cosine, now imagine this function being half a wave, and then also that you can add infinitely many of those by increasing the distance from the origin of the originalist place until it becomes a flat line. So all of a sudden you have this family of functions, kind of like a sinusoidal curve. It's this smooth sawtooth curve that's pretty much straight lines and just met in the middle, and then it drops down. But the idea is to figure out then, we have analytical properties about 1 over x that are different than just the absolute value of x equals y or something like that for between 0 and 2 or something like that. A sawtooth that is not smooth, or that has a right angle, or otherwise not a smooth curve, in terms of that this curve begins at the very, very end at the tip of the tooth and is round there and comes back around and down. So back then to this idea in the quadrant, and what is this for? It's like, well, I want to use this to describe an infinite family of functions that, just like Fourier is an analysis in a sense, ends up building up identities and analytical character about how to sum those, or what the series could be as off those, to make for some systems in differential equations. And why would this be relevant? So, well, first the idea is to figure out how it's relevant, just this sawtooth family. But that might not really have anything that you can add up in terms of, well, how is that not non-standard? It's like, well, you just kind of model as non-standard, because otherwise it would have to be piecewise. And so the idea would be a function here and there, and you'd have absolutes everywhere. The idea is to kind of just keep it in terms of the area that is so built up like that is a function. But then if you had a family of functions between this and that, then you could figure that in terms of that just being the amplitudes, then you could also figure out how to shift those left and right a bit. Well, how are you going to shift them left and right a bit in terms of amplitudes and the periods and pi over a, and making it so that for example, that the functions are orthogonal and the functions are complete, because then it would admit that they have these properties of making transforms in time and frequency domain, and also be possible to define and describe how to make series out of them that approximate or build, when the series exists in any given bounded domain, any other function, and then to work up for what analytical character that might have, that if you can figure out this method of series for those, and it means to compute the coefficients for those, then it's a quick way to provide what might be more suitable for some kinds of functions that look like sawtooth functions, or that have really natural things, their area and what that are kind of described like to sew as a thing, and even just as an exercise, because from reading the development of the Fourier series, these are the desiderata and requirements of providing the exact same set of results. Gets into a lot of things. Now, another desiderata and requirement of such a thing is that, and everybody knows it and spent a couple of years in school picking up the preliminaries to have it, so then they all have one. So when you write it down, it's not a 2-year class for them to read the next sentence. But at the same time, it's, in case you already know that part, it can be old hat. Here and it kind of looks like old hat. A triangular hat. Hat series. So given that as kind of an idea what I'm looking at, then there's 1 over x. And so 1 over x is kind of looked at because what's the inverse function, and inverses are cool. And then it goes through 1 over 1, and it's symmetrical about x equals y, or f of x equals x. It's symmetrical about that. And so if you consider it in terms of even and odd functions, and or f of negative x equals negative f of x, and this kind of stuff, then in terms of otherwise these symmetries, you can work up anything to do with algebraic translations, transformations, or the affine from geometry, say. Well, the idea is to figure out for the affine in geometry, and then how to place small placeholders of substitutions of variables that collect these things to make it so for work and shake things out as a series, and then just apply some modifiers to those and end up having something that's quick to unroll and unroll and crunch and compute. These are the kinds of things that get into the differential geometry. This book here, this curved surfaces and manifolds, when we're looking at that, and they get into the submersions and immersions, that's a whole lot of the idea of that is like, hey, I know you can make an infinite series, and we don't really have infinite time to compute the infinite series, and we don't really want it to be imprecise or not have a closed form. So if you can find some of these cases where the linearizations actually are closed forms for these systems because they happen to, there's some families of functions that they do model accurately, besides the whole general apparatus that any function can be written as this infinite series or so. We have some functions we want to write just as finite series, so we want a whole grab bag toolkit of different ways we can compute the coefficients of infinite series. So if we happen to be able to find one that's finite, then we can write that we're done and get a correct answer. These are the kinds of things that go into reasoning why in terms of the differential toolkit and methods of computing the values that we want to get into stuff like that. So from 1 over x, then the idea is, well, what about 1 over x and that it's symmetrical about this? And it's like, well, I'm not too sure, but there are a lot of things that have to do with it. For example, this integral is natural logarithm of x plus constant. And the integral of that is something like x times ln x quantity minus 1. Well, ln x minus 1, but we have this box at 1.1 here, 1, here, and that is kind of our origin. If you kind of say, that x, if you say for x minus 1, 1 plus x minus 1 over that, is about the transformation of coordinates to the result that's also in the origin, because then you want to be able to do original analysis about the even and odd in terms of that, except instead of the even and odd functions, what it is it's symmetrical about x equals y, compared to things that are symmetrical about the axis. But this is symmetrical about x equals y on the positive numbers. Compared to that y equals x squared, it's symmetrical about the axis. Y equals x cubed, well, it's an odd function. It's, an even function is symmetrical about the axis. An odd function is not symmetrical about the axis. It's symmetrical, it's anti-symmetrical about the axis. These are the kind of things that can then go a long ways, because I don't know too many people who develop theorems and series for positive numbers in these functions to implement and develop transforms, with the idea of then taking this non-standard view, because, well, it starts with this 1 1 over x, and it's symmetrical about x equals y, and it goes through 1, comma 1. And what about one that goes through then other points on x equals y? And then there's also functions that kind of come from infinity and 0 and go to 0, comma infinity, or vice versa. Functions that go to infinity. Meaning that as the domain is increased unboundedly, the range is increased unboundedly. The function is divergent. Well, it goes to infinity. But what can be said about a function like e to the x, which at one is, or excuse me, how about something like x squared? So x starting the fx or y equals x squared. So now this function in the positive numbers has the other side of it is x to the 1/2 or square root of x. And so these two, if you draw them together, those make both sides of something that is symmetrical about x equals y. And as one of them goes from, as they go from to infinity, they go to infinity, although one kind of goes to the root of infinity and the other one goes to the square, you know. But at the same time, then they represent a way to figure out a way to track. Now, if you take that again, this 3/4 turn, and you put it there, then all of a sudden you can see that those kind of, for this sawtooth wave, this is stuff that comes straight down the middle of the tooth and then goes to the edge of the wave. It fills it in there. And so you can imagine blowing those up, it would fill that space. If you can imagine that as a tooth comes down and goes out to x equals y, then it comes down in that triangle and makes a flat line. And so you can kind of just imagine that it's kind of underexplored, or maybe it's not, that just for positive numbers, just for these systems that are symmetrical about x equals y, that it's possible to figure out how to write and describe in these non-standard approaches how to make up what are differential systems, or rather systems of series that solve the functions, so that then we can compute functions and their integrals and derivatives in terms of many of the same techniques applied to make the Fourier series about sine and cosine, the most well-known orthogonal functions, sine and cosine, from trigonometry since antiquity. The most well-known orthogonal functions. So what I'm looking to is this book from University Mathematical Text, Integration of ODEs. And so this is the ODE course, object of this book. I've been looking at it before. It's from first edition 1939, sixth edition 1952, printed in Great Britain. But these other ones were printed from this University Mathematical Text from the United States and printed in the United States. So what this gets into is families of plane curves. Now I mentioned that's maybe where I start here. And trajectories and level lines and lines of slope on a surface. This is where, besides y equals x, that something like y equals 99x and y equals 1/99th x are similarly so symmetrical about x equals y. And so if you think of those as two functions and a way to stand that so that what the corner is on top and the rest makes some base of a triangle, maintains some analytical character just by where the ends go and towards their relations. This is the idea of a sort of 3/4 planar positive number function space, triangular or trilateral. Families of plane curves, 27. The linear equation, an equation of the type fxy prime plus gxy equals hx, which involves y and y prime linearly, said to be linear, by dividing throughout by fx, may be brought into the standard form y prime plus py equals q. Just a function of y alone. Linear. Since the relation, Bernoulli equation, now that's pretty cool. Change a variable. Now, just recently I've been reading this Fourier analysis and boundary value problems, and before that some of the Hermann's mathematical relativistic jets and mathematical bundles and vector bundles, which gets into a lot of the apparatus of the operator calculus. It's pretty cool. But here at integral curves, 14, section 14, chapter 2, section 14. Families of plane curves. When referred to rectangular axes of coordinates, the equation fxy equals c represents for any definite value the parameter c a plane curve. This is the parameterization of it's a parameterization of the plane curve. Now, I never much learned plane trigonometry or you know the spherical trigonometry bit. It didn't that didn't seem very it seemed very awkward. I felt very awkward about it, so I just kind of ignored it. The equation fxy equals c represents for any definite value the parameter c a plane curve. So writing something parametrically is like y equals mx plus b. What's that? It's the equation of a line, a straight line. And you can also read off some of those parameters and as having well-known geometric and coordinate content. Y, the value on the up and down, equals m, the slope, and its name is rise over run. X, the input or free variable. Y is the dependent variable, and x is the independent variable. Y equals mx plus b, the intercept. And so this is something I spent many months in school computing daily for an hour or two a day, less. Functions of this form and how to resolve this form and how to arrive at from tangent of a derivative of a curve to implement this thing. And it's a good thing to know. But here it's the aggregate of all the values of c for which the equation is possible gives a complete one parameter family of curves. Thus the equation x squared plus y squared equals c, wherein all positive values are in terms assigned to c, represents the family of all circles whose centers are at the origin. Now, how is a circle in this positive number space? Well, it's x squared plus y squared equals c because x and y are only positive numbers. So for this 1 over x, you can also have the quarter circle in the quadrant. And it's symmetrical about x equals y. Thus the equation wherein all positive values are in turn assigned to c represents the family of all circles whose centers are at the origin. How about root x plus root y equals c? How about any x to any power plus y to any power equals c? Symmetrical about x equals y. Wherein all positive values are in turn assigned to c represents the family of all circles whose centers are at the origin. The corresponding differential equation p of xy dx plus q of xy dy equals 0 does not involve the parameter c. It is therefore representative of some different geometrical property or other that is common to all members of the family of curves. Some geometrical property or other. Any pair of values x, y for which p and q have definite real values corresponds to a point in the plane at which the value of the gradient y prime plus dy over dx can be evaluated by means of that differential equation. The only exception to the statement arises when the ratio p over q becomes indeterminate, a case that would be investigated later. Indeterminate is generally 0 over 0. Or often enough anything over 0. But here, for example, in the non-standard, what that would be just kind of the origin of this, the x equals y. And then there's also another notion of, well, what happens when that kind of, you just consider that then with also just scaling it as open and being 1 pi radian instead of just pi halves radian, the right angles of the positive plane. So you have this positive plane, positive quadrant, and then in terms of the symmetry, you open that book as if about x equals y, maintaining all else constant, whereas according to that, it maintains the affine as both sides unhinge together. See, these are examples of perspective and analysis, which then make it plainly mathematical. And why is it not standard? Well, because you can't really see it that way, but you can actually kind of see it that way. It's a matter of perspective. Thus, the integration of the differential equation is equivalent to the geometrical problem of discovering the family of plane curves, the integral curves, such that the gradient at any point xy is an assigned function of the pair of variables xy. So here it's interesting, he talks about the gradient, because in all this world of the partial differential equations, which is like we have an orthonormal vector basis and all our functions defined in terms of e1, e2, and maybe e3. And what this means is we have the entire complement of all the theorems about vector spaces, and we have the entire complement of all the theorems about Stokes and Green. And we can compute the gradient because we can compute the Laplacian, because we can compute each of the 3 partials. And when we can set that up with the constant, we can talk about harmonic functions. And then we can attain to the Poincare sphere. But here the author is describing plane curves, and he's saying the gradient is what solves for both these at the same time. The integral curves, such that the gradient at any point xy is an assigned function of the pair of variables xy. If p and q are 1 valued, then there will be 1 value of y prime, and only one corresponding to any point through which the ratio p over q is determinate. This amounts to the statement that through any point xy in general there passes but one integral curve of a differential equation of the first order and degree. So then that gets into separation of equations, like, well, if you can separate the equations in the first order and degree, then you should be able to figure out these plane integral curves from them. But then also it gets into that, well, for some of the kinds of the higher order ones, then we get into singularities or non-principal values. Or otherwise the bivectors, or anything which makes a doubling space, or anything which in effect is so implemented by any values in algebra. Here though, we've restricted ourselves to positive numbers, so in a sense it gets into like, well, you don't really need complex numbers yet, you can still just kind of resort to negative numbers first. It's like, negative numbers aren't real. Right. But you can use them like complex numbers when you're working in a function space of positive numbers. Well, at least they're not imaginary. It may, however, the symbolic expression of any geometrical problem that involves directly or indirectly the gradient at any point is in fact a differential equation of the first order. It may, however, be of higher degree than the first, but for the moment, problems that lead to equations of the first order and degree will suffice as examples. So here the author makes clear that at least for the first order, it's got a simple case, and then for the higher order, it might have a simple case. If P be any point xy on a plane curve, let variables t and g be the points at which the tangent, ordinate, and normal at P respectively meet the x-axis. So this is like the intercept from the parametric line, and the ordinate is where it drops to, that's x itself. The tangent is that intercept of the line. And the normal is as of the intercept of that line's through that point's a line which has a slope of 1 over the tangent slope. Then if psi is the angle between TP, the TP, that line,